What the heck is bond dipoles? All right, so yesterday we talked about this scale at the very end. Was it 3.3? I forget. I don't have these memorized. Sure, 3.3. Where when elements are compared in a bond, they're connected to each other. Say like you have selenium and bromine connected to each other. You check out their electronegativity and find the difference. So this one, these two have a difference of 0.4, so that means this is polar. All right, what the heck does that even mean? What the heck does that even mean? I don't know if is there any sporty people in, like, does anybody, track and field was canceled this year. I forgot because of COVID, because of the apocalypse, but there's some people who do pole vaulting, where you have a little person right here and they've got the giant stick and they got to hop over the thing onto the mat. I went to a rural school. We did not have anything set up for this. We did not have any pole vaulting equipment. But if you wanted to, you could apply to go into pole vaulting. And the first time you would get to do it is when you actually did it at a competition. So I was not a jumper at all. You could guess that by my body type. I had to train really hard in basketball to jump. I played high school basketball. I could throw things really far. I was hella strong, but I couldn't jump. But some of my friends could jump like crazy. And I remember them trying pole vaulting for the first time without any training, and they nearly killed themselves because there's a lot of technique to it. I think we do have pole vaulting at Lindsay Thurber. I forget. I don't know. I don't know if you can even tell somebody how to do that besides, just stick it in the ground and then hope for the best. But our poles are different. And we're going to look at bond dipoles because when you put them all together, they tell a really cool picture about how a molecule will interact with other molecules. All right, so let's take a look at something real simple. Like, let's say we had an NO bond. No, I know you don't want to do this, but too bad. Nitrogen has an electronegativity of 3. Oxygen has an electronegativity of 3.4. Now, what does that mean? That means that this line, remember, is really 2 electrons that are sharing the same space. This is a covalent system. Really, everything we've talked about so far is a covalent system, non-metals and non-metals. And when you have an unequal sharing, when your electronegativity is different, the oxygen moves the electrons a little bit closer to it, just a little bit. It's like, hey, come here. And nitrogen's like, right? If the difference gets bigger, then the one that has the higher electronegativity pulls it closer. But you wind up with a side that's sigma positive and sigma negative. You have a difference in charge polarity, which means that the overall pull of the molecule is towards the oxygen. You have one side which is positive and one side is negative, kind of like a bar magnet which has north and south on it. There are poles now in this bond. Okay? The greater the difference, the greater the pole difference. And when you have something that has the same electronegativity, like sulfur hooked up with selenium, they're both 2.6. This little stupid thing, you never have to worry about the sigma thing. It's equal. It's non-polar. Okay? Now, that's for very, very simple systems. We're going to take a look at bigger molecules, right? Because very few molecules are diatomic, just 2. How do you tell if this molecule is polar? And what does it even mean to be polar? What the heck does that even mean? If a molecule is polar and you have another molecule that's polar, what happens is the ends that are close to each other that have difference in polarity are attracted to one another. And this is a type of bonding that we're going to talk about a little bit later. But this type of bonding means that those two are attracted to each other and they will hold each other together tighter than a non-polar molecule. So polar molecules generally hold each other together tighter. So their boiling point and melting point is higher. Another thing that happens is, for example, water, and we'll talk about water in a second. Water is a polar liquid, and things that are polar attract things that are polar and allows water to dissolve anything that's charged or anything that's polar. In order to figure out if a molecule is polar, as opposed to just two little atoms compared to each other, we need to do a couple things. First off, the drawing of the molecule needs to be appropriate, which means that you need to use the proper stereochemistry to figure out if a molecule is going to be polar or not. Then you need to put down the electronegativity. As you get better, you can skip some of these steps. So this is like a big puzzle. I love this. This is a really fun part of chemistry for me in university. So carbon's 2.6, hydrogen is 2.2, right? Okay. So each of these bonds, right? This bond, this bond, this bond, and this bond are all polar. But there's a trick to it. So I'm going to get rid of all of these little line things. Okay. Hydrogen, in this case, is sigma positive because it's got a lower electronegativity. The electrons are going to be pulled more to the carbon. So it is true that this bond, this hydrogen-carbon bond, is polar. And we're going to have a pull into the carbon. Over here, it's the exact same thing. Now I'm going to use a different line instead of the dark line. So it's a little easier to see. So that's polar, that's polar, that's polar, that's polar. Now I got a question for you. If you had four cars coming at each other in four different equal directions with equal speed and equal weight, and they all smashed into each other, would that smash move? Think of it from a physics point of view. And the answer is, in a tetrahedral, because that's equal four, right? Four molecules is an even number, and they're equal poles, they all cancel out. This push in is canceled by this push in. Think if you're shoving somebody of equal strength, of equal weight, do you move anywhere? No. This one pushes in, and this one pushes in. So this molecule, while individual bonds are polar, and it's got four individual polar bonds, the molecule itself is nonpolar because all the dipoles, these little arrows are called dipoles. All of these cancel out. Okay, now let's take a look at this molecule, NH3. All right, let's write down what we know. Nitrogen has an electronegativity of 3. Hydrogen has an electronegativity of 2.2. Okay, so where are the arrows going? All right, into the nitrogen. Right? Okay, now I'm going to get rid of those and write it in some different colors. Into the nitrogen. In. What's different about these arrows than the other ones? Is there an arrow that's going in that's not being deflected or opposed? This one, right? You could say these two, they're going in like this, and maybe they cancel each other out, but this one doesn't. It has a pole that goes straight through the molecule without any impedance by any other arrow. Right? Even these are not the same angle, right? They're not coming at each other like a tetrahedral. So that looks messy, but if I redraw my arrow, it's going to look like this. What does that mean? That means this molecule is polar. The electrons are going to be pulled to the top, leaving the bottom positive. Like a magnet, ammonia can connect to other ammonias and keep itself together. So ammonia has a much higher boiling point than CH4 because of that. Okay. Now, when we mark this or we care about this, I think it's on the assignment. I mark this, and Zelinsky will mark this in a grid. So as long as your arrow is in the right grid, you get the mark, like the overall arrow. And look how easy it is, right? Like, do you think that makes any sense? No. Right? What about this? No. What about that? No. The only plate, like if it's off a little bit, who cares? As long as it's in the right quadrant. Okay. How about water? The greatest polar molecule on Earth. Now, if you draw water like this, you have forgotten the stereochemical rules for water. You have forgotten that water has two big lone pairs which smush water into a bent or angular molecule. So if I had forgotten to draw it this way, and I put down my electronegativities of 3.4 and 2.2, you would say those arrows are equal and they're coming in at the same angle, and water is nonpolar. And that's not true. Now, when I look at this, I've got an arrow going here and an arrow going there. Now, those aren't the same angle. They're not coming in at the same angle, right? Think of a car that's coming in at an angle, hitting another car that's coming in at an angle, not a head-on, but an angle. Where does physics tell us the overall force will go? And the answer is they'll kind of smash and go straight up. So that's why water is a polar molecule. Around the oxygen, it's really negative, and around kind of the middle of the hydrogens, it's really positive. Because electrons, we draw them as a dot, but they're really a packet of energy. They don't stay in one place. They're not like fixed like a dot that doesn't move. So it creates a quantum state of positivity and a quantum state of negativity. Really complicated, I know, but that's how it works. Now, linear molecules are almost always nonpolar. Right? So if you have a linear molecule and we draw our arrows, this one seems like it's a little different because the arrows are going away. But think of yourself as, we do this with ropes, actually, when the class is in session. I have all these ropes and kids hold the ropes. So if you're beryllium, think of you being beryllium and then there's another kid on either end, and you've got ropes and they're equally tugging you. Do you move either way, or do you stand right there because they're equally tugging you? And the answer is these cancel out. They're nonpolar. But let's say I had beryllium fluoride with bromide. Bromine or bromide, bromine is 3.0, fluorine is 4.0, and beryllium has a really low electronegativity of 1.6. So we'd have a dipole arrow going here and a dipole arrow going here. Now, look at the difference between here versus here. That's an unequal pull. Think of that like a tug of war. Your beryllium, bromine's tugging on you, and then you get yeeted by fluorine. Like you just go frickin' flying. Okay? This is like somebody Mr. Z size tugging on you, and this is somebody, I don't know, you can think somebody medium sized like Z-Dog tugging on you. So probably I could make everybody go flying. So unequal pulling allows polarity to occur. The polarity in this molecule would be straight to the fluorine. Okay. All right. Let's do, yeah, this is important. We'll do this one, this PCl3. Okay. So what would PCl3 look like? Well, we have to draw it in proper stereochemical shapes. Nitrogen with three things around it is a pyramid. Is phosphorus in nitrogen's category? The answer is yes. Phosphorus is in nitrogen's category. So we would draw this like a pyramid, the dotted line, and then we would write our electronegativities in. Phosphorus is 2.2, and chlorine I think is 3.4. 3.2, I'm wrong. So all of our little dipole arrows will go like this: out, out, and out. Is there an unequal pull? Is there anything pulling from the top, right? Nothing's pulling up this way. Everything's going down. You could say these are maybe going to kind of slow each other down, but look, this one is left alone. So the overall polarity goes through a chlorine, right? It wouldn't make sense to say the overall polarity is this way, right? Does that make any sense where all the arrows are going? No. Does it make sense to have it this way? Absolutely not. So that molecule is polar. That molecule is a polar molecule. All right, one more. What about this guy, SO3? Okay, it's a weird molecule. Sulfur's 2.6, oxygen's 3.4. Oh, look, it's the same idea. Down towards the oxygen. Okay, that's the break for now. You now have everything you need to know for the assignment that's due at the end of this week. I've left this to last, and now you can fill in your polarity arrows on that very last question. Okay, that's it.